Okay, next we'll talk about a really good sorting algorithm called Quicksort. And Quicksort happens to be recursive. So we know a little bit about bubble sort. Bubble sort is a big O of n squared algorithm. So let's review bubble sort. Okay, so basically what happens in bubble sort is we look at each pair of numbers, adjacent pair, the numbers that are right next to each other, and we say, well, if the left one is greater than the right one, then we're going to swap. Right? So code-wise, that would look something like this. So let's say this was a vector here called vec. And what we're going to do inside the loop is we're going to check to see if, actually this should be a -1 there, if vec at I is greater than vec at I plus 1. If that's true, we are going to swap the elements at I and I plus 1. Okay, so the reason this is supposed to be vec.size -1 is we're going to add 1 to I, and we want to make sure we stop 1 short of the last item, because when we do I plus 1, we want that to be the last item. Okay, so what happens, of course, if we do this, so we look at each pair, and if the left is greater than the right, we swap them. And then we do that again with the next pair and the next pair. And if you go through this exactly 1 time, the largest value will move or bubble to the end. Okay, and after the first iteration, after we do that exactly 1 time, okay, what's going to happen is this is going to be the largest item. And if we know the largest item is there, we can actually say that, well, this part of the list is sorted, and this part over here is unsorted. Right? Okay. So that's after doing this once. If we do this again, okay, we do this again. Now the second largest item is going to go here. And now that we know the second largest item is there and the largest item is there, again, this is the sorted section of the list, and this is unsorted. And this process repeats. Right? If we do this again, this will be the third largest item. And we know this is the second, and this is the first largest. So this is the sorted part of the list, and this is unsorted. Okay, so each iteration of the inner loop takes n-1 iterations to bubble the next largest element to its final sorted position. And if we have to do this 1 time to sort 1 item, if we do that about n times, it turns out to be n-1 times, then the entire collection will be sorted. Okay, so we have the n-1 of these critical operations that happens each time just to bubble the largest item to its next position. And we have to do that about n times, turns out to be n-1 times, in order to get all the items in their final sorted position. Well, this becomes, if you do the math here, it's n squared minus 2n plus 1, which we know in big O we ignore all the smaller terms, and what we say is bubble sort is a n-squared algorithm. Now when n is large, this becomes a very expensive way to sort. Now we're going to talk about Quicksort. Quicksort is a sorting algorithm that at the worst is n-squared, but on average, Quicksort is a big O of n log n. Okay, so bubble sort, n squared, Quicksort, n log n. Let's look at the difference between these two algorithms in terms of just raw numbers here. So let's say let's have a column for n. We'll have n squared and n log n. Okay, so our n's will start small. We'll go 10, 100, 1,000, a million. Okay, so 10 squared is 100. 100 squared is 10,000. 1,000 squared is a million. 1,000 thousands is a million. And 1 million squared is 1 trillion. That's a lot of zeros. Okay, so if we were sorting, a million names in a phone book in a large metropolitan area, that's not unusual to have a million names. To sort would take 1 trillion iterations, okay, or 1 trillion of these comparisons here. This is the critical operation of this algorithm, comparing two values that are right next to each other. So a million names, we have to do 1 trillion comparisons. Let's compare this with n log n. Okay, so the log of n, right? So these are always base 2. Okay. 2 to what power is equal to 10? Well, we know 2 to the third is 8, and 2 to the fourth is 16. So it's somewhere between 3 and 4. So we're going to take 10 and multiply it by log n, and we're going to come up with about 33. Okay, so if we compare these, we'll see, yeah, this is smaller. How about n log n when n is equal to 100? Well, that's about 664. N log n when n is equal to 1,000. About 9965. And the really impressive one here is when n is a million, n log n is about 20 million. Okay, just look at the ratios here between the values. This is growing quite fast compared to these. Right? So a million names, it only takes 20 million of those critical operations to sort the names, where it took 1 trillion before. The difference between 20 million and 1 trillion is just enormous. And in fact, if you were to graph n squared looks something like this. It grows pretty quickly as n gets big, whereas n log n still grows, but it grows much more slowly. Okay, so as n pushes out farther and farther over here, there's just a dramatic difference between an n squared algorithm and an n log n algorithm. Okay, so let's take a look at Quicksort. Quicksort is deceptively simple, and actually it's not really that deceptive. It's just you'd think an algorithm so much better than bubble sort would be complicated. When we look at the code in a second, you'll see it's really not that complicated. There's really 3 steps to Quicksort. The first is to pick an item in your array that you're going to be sorting and call that the pivot. Okay, so let's draw a couple items here. So we have 17, 12, 34, 30, 7, 10, and 20. So this is my unsorted collection of numbers. Okay. The first step says to just kind of pick an item at random and call that the pivot. Well, rather than actually choosing a random number, I'm just going to select the first one. The first item in the vector or the array is always going to be the pivot value. Okay, so in this case, 17 is our pivot value. Okay, the next step says we need to partition the items around the pivot. In other words, we want to move all the other values in the list around that pivot. Okay, so let's take a look at what's going to happen here. The items to the left of the pivot are going to be less than or equal to the pivot, and we're going to call that partition 1. And the items that are greater than the pivot value are going to be on the right side, which we're going to call partition 2. So what we need to do is to transform this okay. So 17 is the pivot value. If we were to partition this, we need to take all the values that are less than or equal to 17 and put them on the left-hand side. So 12, 7, and 10 are the values that are less than or equal to 17. And the values that are greater than 17 are 34, 30, and 20. Okay, so that's this idea of partitioning. Okay. And what you notice is the pivot value always ends up in its final sorted position. So if we move everything less than or equal to the pivot value to the left and everything greater to the right, what that means is that the pivot is going to be in its final sorted position. Okay. And we also have what we're calling two partitions. Partition 1 is over there, and partition 2 is over here. Okay. Now the last step is to use recursion to sort partition 1 and partition 2. Now each of these two partitions are smaller versions of the original problem. They're smaller lists or arrays or vectors. And we know about recursion, the hallmark to a recursive algorithm is we take a big problem and we break it into a smaller version of itself and we recurse. Okay? And that really is the entire algorithm. Okay? So let's look at the Quicksort method. Quicksort takes in an array and a first and a last value. Array is an array or a vector of ints, but it could be an array of anything. Okay, I just happen to make it ints and make it a plain old array instead of a vector. First and last are the positions of the beginning and ending part of the array. So when we recursively sort this partition, we're going to call this first and this last. Right? And then when we recursively handle partition 2, we're going to call this first and this last. Okay, so these are just index values to point to the beginning and end of the sublists. Okay, now, of course, in a recursive solution, we always have to think of the base case and the general case. The base case is basically when we have a list with one item on it. A list with one item, by definition, is sorted. There's nothing to move around. Okay, so if the first is less than the last, that means we have a list that has more than one item in it. So here F is less than L, and F is less than L here. So these are lists that have more than one item on them. If first is ever equal to last, right? That's our base case, and we know there's only one item in the list, and it's already sorted. In this case, in the base case, there's not really anything we need to do. We just can kind of return from where the function was called. But in the general case, when first is less than last, that means there are more than one item that need to be sorted. What we're going to do is we're going to partition. Okay, so what it means to partition is to move the pivot value to its final sorted position, move all the elements around it, right? So we have elements less than or equal to the pivot go on the left, elements greater than the pivot end up on the right, and then we're going to return the position of the pivot. We need that position when we make our recursive calls below. Okay, so calling this partition function, I'm not going to cover this in much detail right now, but that just picks the first item, calls that the pivot, and then moves everything around that pivot value. Okay, and the partition function will tell us what is the position of the pivot. Then what we do is we just recursively call Quicksort, and for the left partition, partition 1, we start at first and go to pivot position -1. Right. So here's first, and pivot position -1 is going to be that one there. So that's our first, that's our last. Okay. Then we recursively do the same thing again, but this time we say pivot +1 and last. So if this is our pivot value, pivot +1 is here, and last is here. Right. Okay. And that's it. That's the entire algorithm. Okay. So this must seem too simple. Okay. To me it seems kind of simple. We haven't talked about how to partition, of course, but that's just moving things around the pivot value in a list, and it shouldn't be that hard. So like I said, I'm not going to talk too much about partition. What might be confusing is, well, why is this so much better than bubble sort? You notice there's not a lot of code. There's only basically 4 lines of code, whereas bubble sort is around the same length, maybe even a little bit longer. Okay, the key to understanding Quicksort is to kind of view the picture that I'm about to draw here. Okay. Okay, when we call Quicksort and we pass in a vector or an array, what we get is this partition value. Okay. And in the examples I'm drawing, the pivot value lands in the middle. Now that's not always going to happen. That's kind of like the best case scenario, is when the value you pick here just happens to land somewhere in the middle, and we have about equal sized partitions on either side of it. It's not always going to happen, but on average it happens a good amount of time. So what happens when we call Quicksort one time? Well, one item gets sorted. Right. And then we recursively do the exact same thing with the 2 subpartitions, so the left and the right. Okay, and what's going to happen here? We're going to do the exact same thing. We're going to call the partition function. Okay, but now on these 2 sublists, now we're going to sort 2 items. Right. And then what are we going to do there? Well, we're going to send these subpartitions. Right. So here's those 2. Here's these 2. And we're going to do the exact same thing. We're going to partition. Okay. Now notice 4 items got sorted. And then, of course, we'll do this again. Each one of these will be a sub-partition. For each one, we'll partition. We'll move that partition value to its final sorted position. And here we have potential to sort 8 items. Okay, so each level requires about n critical operations to move the values around the various pivot points. But unlike bubble sort, there are an exponential number of items that get sorted at each level in the recursion tree. Okay, so at the first level, right, we picked the first value and we partitioned, right? We moved all the things that are less than or equal to that value over here, and all the values that are greater to that pivot value we moved over here. That required us going through all n items to do that partition. Now on the second level, remember we have this recursive call, and the order the recursion happens is actually more like this. Right, the order that I drew those lines. But you can, what I want you to do is think about them as kind of happening at the level, here's the first level, the second level, the third level, the fourth level. Well, in order to partition these two chunks, again, it took about n comparisons, about n critical operations to partition this chunk, and it took, this would be n over 2, because we're about half the size of the original. It took about n over 2 critical operations to partition this chunk, and about n over 2 critical operations to partition this chunk. And over here it took about n over 4, n over 4, n over 4. These all sum up to, the partition takes about n items at each level. Okay. Even here, when we have 8 little chunks, if we looked at the amount of work it takes to partition each one of these 8 chunks, if you sum it all up, it's about n items. Okay, but on the first level, 1 item got sorted for those n critical operations of the partitioning. On the second level, 2 items got sorted for n critical operations of the partitioning. Right, so there were 2 partitions at the second level, but they summed up to be about the same work to partition as on the first level. And on the third level, 4 items got sorted, and so on. So there are about n critical operations at each level to partition all the little chunks. Right? So at each level, there's about the same amount of work needed to partition. And at each level, the number of items that actually get sorted doubles. And this doubling behavior is characteristic of a logarithmic algorithm. Okay, so at each level, we have the partitioning takes about n operations. Okay, how many times do we have to do this? Well, not n times. Now, because we get that doubling behavior, it's really log n. Okay, and this is how we come up with this n log n classification for Quicksort. Right, because we're going through all these elements, but we only have to do it about log n times. Whereas with bubble sort, we similarly had to go through all the items, but we had to do it n times, and that was n squared. Well, now, since we're doubling the number of items that potentially get sorted each time, we only have to do that on average about log n times. And that's much, much better when n gets large. Now, the worst case performance of Quicksort is when the list is already or mostly sorted. Let me show you that example. So let's say we had a list and we wanted to sort it, but just coincidentally all the items were already sorted. So maybe we didn't know that ahead of time. If we called Quicksort, our partition value would result in there's not really anything to the left here. So this would kind of be empty, but then we'd have a right value. Okay, and we'd partition again. Again, there's nothing to the left. When we partition to the right, we would have this. When we partition this, again, there's nothing there. Okay, we'd partition this. There's nothing to the left. Okay, finally, we get to a list with one element. There's nothing to partition there. Okay, and here it took n critical operations on each level to do the partitioning, but now it required all n levels in order to actually sort the already sorted list. So when a list is mostly sorted, Quicksort does not perform well. Okay, it's actually a big O of n squared algorithm. So there are actually other algorithms that do better when your list is mostly sorted, or if you know your list is sorted, you shouldn't be calling sort at all. Quicksort works best when the maximum number of sortings happen at each level, and this happens when each partition is roughly the same size. In other words, when the pivot lands somewhere in the middle half of the list. Right, so no matter what our list looks like, right, this is the middle part of this list. Okay. When we select a partition value and it happens to land in the middle, that's when we get our best performance. Okay, because when the pivot lands in the middle, about twice as many elements will become sorted in the next recursive call. Now, a random list of sorted numbers has a 50-50 chance of landing in the middle. So half the time we're going to get the optimal recursive performance, and the other half we won't. On average, though, we say that Quicksort is a n log n algorithm. Because remember, we factor out or we ignore the smaller order terms, and in this case, it kind of averages out to n log n. Now, I said I wasn't going to talk a whole lot about partitioning, and I'm not going to. I won't go into the exact details of the partition function, but all you really need to do is make the first element the pivot value, and then move all the other values around it. Right, so I kind of glossed over this function called partition. I'm going to leave this as an exercise for you to complete, where you pass in an array and a first and a last value. You should be able to swap things around so that all the values that are left of the less than or equal to the pivot value will be to the left, and those greater will be to the right. Okay, so that's Quicksort. It looks quite simple, and it is quite simple if you could wrap your brain around the recursive nature of this particular algorithm. It's actually an excellent algorithm for sorting. When n gets large, you should definitely be using Quicksort and not bubble sort.